Okay. Okay. This I can tell the person mentors. Okay, let's continue. Now, let's do a recap of the last class. Now, I want also to make you understand that whenever we are talking about assignments, don't go online to get any information for the assignments. Every assignment you're given is what you can access from your slides. So you must make sure that you sort out your assignment from the information that was taught in the class. So when you go online to solve the assignment, I will know and I will not do it. Or any course I'm teaching you, don't go online. Except I'm asking you, I'm giving you an assignment that you have to go and investigate for. But if it's an assignment that's supposed to be a classwork, remember, our classwork is meant to be what was taught in the class. So that has been so because we are online, that's why I'm giving you toys to go home. On a normal day, you're supposed to do it inside the class and submit the way we normally do in 322. So I will not give you an assignment to go and start googling. So making a recap of the last class. Virtually, we are talking about classes of terpenes. In the last class, we talk about monoterpene. We'll talk about the precursor for terpenes, for monoterpenes, precursor for diterpene, sesquiterpene, and I also say you must know the precursor for steroid, triterpenoid and steroids. They are from spelling, and you must know it. Then I went further to also let you to know that the basic units of all terpenes are 2-methylbutadiene, which is the isoprene unit. Isoprene unit, the IUPAC name is 2-methylbutadiene. Then we went further to talk about examples of monoterpenes. We'll talk about that we have acyclic, we have monocyclic, we have bicyclic. And for the sake of this class, you're going to just don't go beyond bicyclic. Acyclic is a ring that is not closed. It's an open ring. While monocyclic is an open ring that has only one ring. A bicyclic is a ring that has another ring inserted in one ring. So that's why we have something like alpha-2-gene, we have alpha-pinene, we have camphin. So these are bicyclic. So all the assignments I gave you is what you can get here. Then if the question is monocyclic or monoterpene, it means that you can use anyone that is. If the question is monoterpenoid, it means that you must use the one that has oxygen as a functional group, either in the form of carboxylic acid, but from here we have in form of alcohol and aldehyde. And I told you that whenever you know one, you've known another in terms of acyclic. If you know geranyl, you can know nerol, and you can also know geranyl and neral. So these things are what, in fact, when you know neral, you can also know citronellal, because difference is hydrogenation. From neral, you can form your citronellal, because difference between neral and citronellal is just hydrogenation. The double bond becomes saturated. So with having non-one geranyl, you can generate so many compounds under a cyclic monoterpenes. Then when you come to cyclic monoterpenes, I give you an example that when you have your menthol, you've known your menthol. So with this, you've generated 2. Then the another one you can know is something like camphor. You have 3 already. So I'm trying to give you the simple method you can use to answer these questions when you talk about structures of common monoterpenes. Remember, you have to understand them. Then you're talking about bicyclic. You can talk about, remember, in a bicyclic, like I said, according to bicyclic, a typical example is what? Camphor. But if you're talking about, now, if they say monocyclic, it means that you're dealing with one that has one ring. If you're talking about bicyclics, you have 2 rings. So we have Tujun as a bicyclic too, because there is another ring inside Tujun. Vebanun, Fenchun, all these are bicyclic. So just be able to know that you can be able to know like 2. Like Tujun and Camphor is a typical example of bicyclic. You're good to go. Now, from there, we'll talk about the physical properties of monoterpenes. Just know that some of them, they are mostly liquid. Only few of them are solid. That's what we'll talk about camphor. You know camphor in the market. That's why the smell of that camphor repels some insects. So they are essential oils. Now we'll talk about if some of these things occur in plants and animals. And in animal is what they use to shield themselves from predators. So that's why animals, some of them, something like all these alligators, whenever there are predators, they will exhibit that essential oils. So at times you see that some of their smell will repel you. The essence is that they want to scare you away from attacking them. Then in today's class, we're going to talk about how do we synthesize monoterpenes. Example is to talk about in that of, like you can say, structural elucidation. Now, whenever we are talking about structural elucidation, we are trying to tell you that this is a means you can know that this is the compound. How do I know that Eniola Israel is a boy? Eniola Israel is a boy because when I look at him, he did not open earring. Not in the days of today where guys are wearing earring. He's not. I can see he has biabia. If I look at his shirt, there's no sign that he has breast. So he's a boy. So elucidation is if I see a compound, what are the reactions that can validate the identity of this compound? If I see a compound that has hydroxy group, I'll validate the hydroxy group by undergoing oxidation, because that hydroxy group is going to form aldehyde or ketone, depending on the nature of the hydroxy group. If I see a compound that has unsaturation, how will I say this compound has unsaturation? If I do hydrogenation and that double bond disappears, I've validated the presence of unsaturation. So these are what we talk about, how to elucidate a structure, is what are the reactions that will confirm the identity of that compound. So in this synthesis of camphor, we want to use some compound to synthesize camphor. In that case, we are going to elucidate the structure of camphor. Now, whenever you want to write this in exam, what you need to know is your starting material. Now, I want us to follow it sequentially for you to understand. Now, look at our starting material here is alpha pinene. My question, alpha pinene, is it mono or bicyclic monoterpene? Anybody can answer.
Bicyclic.
Bicyclic.
Bicyclic. Because there is another ring inside one ring. You can see that ring was highlighted, right? Now, in that bicyclic, is it on cis or trans? What we are having, is it cis or trans?
Cis.
Is it cis? Now, whenever you see a compound, remember what makes cis or trans is the substituents. Because one of the substituents are dotted, it means it's not in the same direction. If all of them are have the same sign, it means they're on the same direction. Remember, cis is when they're on the same direction. But because one is highlighted and another one is dotted, meaning they're not on the same phase. So this alpha pinene is a trans isomer. Now, the first reaction that occurs is with titanium oxide hydrated, meaning that this titanium oxide that's supposed to be in powder is not in powder again. There is water in it. So this is hydrated titanium oxide being heated up at a very high temperature of 180. What happened? My alpha pinene will be translated to what? Camphene. Now, if you look at what happened here, is there is rearrangement. The double bond has rearranged. You can see where the double bond was, it has changed now and connect to that methyl group, making that methyl group methylene. So first thing that happened, that was transition from alpha pinene to camphene. Then when I do acidification, remember in the presence of an acid, then we are going to form an ester, like esterification. Now, from alpha pinene, we are going to form camphene, and then we'll form isobonyl ethanoate, which is an ester. Now, under hydrolysis of this ester, what happens? Remember, esterification, the reversible reaction is hydrolysis. So when we hydrolyze, the ester aspect of this compound is going to cleave away. We are going to form an alcohol. Then when we oxidize, we form our camphor. Now, if you look at this, this reaction is also occurring where there is presence of double bond. That is where that is the reactive. Remember, when you talk about reaction, you talk about the functional group. In this alpha pinene, the only functional group we have is double bonded. So every reaction is occurring at that functional group from beginning to the end. So in synthesis of camphor, alpha pinene under hydrated titanium oxide at high temperature of 180 is going to translate to camphene. The camphene under esterification reaction is going to form isobonyl ethanoate, which hydrolyzes to isobonyl and oxidizes to ethanol. Oxidizes to camphor. So the only place the reaction is occurring is on that double bond. So everything occurs there. So how many steps do we have in this reaction? We have 4 steps. The first one is titanium oxide that will translate alpha pinene to camphene. Then secondly, esterification that will form an ester. Then when hydrolyzed, we form an alcohol. Then under oxidation, we form camphor. Can we relate to this? Is it something we can relate to? Ask question on this before we further. Please, the most important thing when you get home today, make sure you lay your hands on how to draw. Because this course is an easy course. But you must be familiar with drawing. Don't read without having biro and paper. Like I said, you must make sure you don't read chemistry without writing things down. Because when you don't write, you feel you know it. But when it's time for you to write, you realize that we don't even know what you felt you know. Please, like this alpha pinene, draw the structure. And when you talk about camphene, draw. Because if you've gotten the structure of camphene, every other thing follows. Because that structure of camphene is still the same thing, just a rearrangement of that ring that contains methyl group until you form your camphor. And remember, when you know this camphor, you're going to also know camphor as a bicyclic monoterpene. So if there is no question, can we move to the next slide? Synthesis of camphor. Allow. Continue. Next slide. Okay. Now, in this slide, we are talking about enolization equilibration of cis and trans dihydropylegon. Now, if you look at this compound, what we are talking about is that from this pylegon, I can have cis or trans. Remember what the cis and trans, you can see what I'm talking, you can see what happened to cis and trans. What's different between them? Different between them is that the cis has everything stressed, but the trans, one of them was dotted. So then they're asking you that now, if I want to move from a positive and negative, positive pylegon to dihydro, what am I doing? What happens in dihydro? In that reaction, what happens? When you see hydrogen in palladium and carbon as a catalyst, what is happening?
Hydrogenation.
Is hydrogenation. When we hydrogenate, we are going to have dihydro. Now, in this dihydro, now the last compound, last scheme is showing you that I can move from cis to trans using acetic acid and triose carbonate, potassium triose carbonate. So these are the reagents that can translate from one isomer to another of this compound. So if the question says, show a scheme of that show a reaction scheme that indicates transition of cis dihydropylagon to trans isomer, or that shows the transition of isomers of dihydropylagon. That is what we expected to, right? So it's a very simple one. So nobody expects you to cram anything. Just understand what is happening. We are trying to make them to be in equilibrium. Remember, equilibrium means that this is a reversible reaction. So if I put this reaction, if I put this, it can go forward or backward. So that is what the slide is talking about. Next slide. This is an alcohol. Who can remind me where you've seen this particular slide before? Where did you see this slide before?
213.
213, yes. It is in 213. When we are talking about oxidation. Now, remember we talked about in that 213 that whenever you want to do selective oxidation reaction, you are going to use PCC. Any other oxidation must translate alcohol to carboxylic acid. Now, that's what this slide is talking about. So whenever I want to do my oxidation and my target compound is an aldehyde, I don't use any oxidizing agent that has to do with complete oxidation. So I cannot use potassium permanganate. And I cannot use chromic acid because they are going to give me complete oxidation. So when I'm looking for limited oxidation that can only give you one step, I'll use pyridinium chlorochromate, which is PCC in DCM. So that is what the slide is talking about. Just remind you about the selective oxidation. So a scheme can come up and bring a reaction like citronenol to tell you how do you convert this citronenol to citronenal. How do you do the conversion? Some of you will go and use potassium permanganate. If this scheme is put and in the middle of range and nothing is done, we look at alcohol, look at aldehyde, I say, this is oxidation. And please, whenever you're writing a scheme of oxidation, don't put oxygen in brackets. Use a selective oxidizing agent because you know what you're doing. So in this scheme, if something like this comes out and you go and put oxygen in brackets, there's no mark for you. Because you want to do Agbari, you have to tell us that you know what you're dealing, that this is selective oxidation. So you're going to use PCC in DCM. So nobody expects you to write the structure of PCC. But for you to understand what PCC contains, that's the sense of the structure under. But the most important thing, understand that whenever I'm doing selective oxidation, that I don't want my alcohol to form carboxylic acid because primary alcohol under oxidation forms carboxylic acid. So when my target is not to end up in carboxylic acid, I do selective oxidation. And in doing selective oxidation, I need PCC, pyridinium chlorochromate. You should be able to know the name. Because remember, you guys are on the last plate as chemists. The next slide. Any question? Now, these are the reactions of citral. Now, the question can be, how do you elucidate citral? Meaning, what are the reactions that validate citral? Remember, from the reactions we are talking about, we can say that from nerol or geraniol, we can get citral or neral. So you see the same thing we are talking about here. The simple reaction is from citral, we do reduction to form what? Neranol. Now look at the first compound we saw here is what? Citronenal. Depending on the kind of reduction you're doing. Now, if my reduction is for double, remember, hydrogenation is a reductive reaction. Hydrogenation is a reductive reaction. So if when I'm hydrogenating, my interest is to remove the unsaturation on citral, I'm going to form what? Citronenal. And if my interest is on the aldehyde, I'm going to form what? Nerol or geranyl. So that's what we call them. This is selective, depending on what you're looking for. Are we understanding the slide? So when I want to do reaction, if I want to do structural elucidation of citral, what I'm expected to do, what is the reaction that can undergo in that citral and what will form? So I can do hydrogenation either to form my citronenal or to form my nerol or geranyl. I am doing the same thing, or structural elucidation, because I'm using this reductive reaction to validate the structure of citral. I'm saying that citral has double bond when I'm forming citronenal. I'm saying that citral has carbonyl compound that can undergo reduction to form alcohol when I'm forming nerol. Let's go to the next slide. This slide is very important. Don't be confused when you look at this slide. So let's follow it one. If you have your biro, if you have your paper, write. Now remember, we just talked about geranyl and nerol. And we are also having another one they call citronenal. Now, what's different between geranyl and citronenal is what? Hydrogenation. In the previous slide, we talked about citral and citronenal. We talk about hydrogenation too. Because in citral, geranyl or nerol has undergone oxidation to form aldehyde. But in this particular scheme, they are still the alcohol functional group. So now, when I want to form my 3,7-dimethyl octanol, I have 3 steps. So you can write from geranyl, I will hydrogenate to form citronenal. From that, I will hydrogenate again to form my what? 3,7-dimethyl octanol. That's 3 steps. So if the reaction said, how do you synthesize the elucidation or synthesis of 3,7-dimethyl octanol from nerol? It's just hydrogenation all the way. When you hydrogenate your geranyl, you're going to form your citronenal, which you're going to hydrogenate further to form your 3,7. What happened? Now, in my geranyl, I have 2 double bonds. When I do the first hydrogenation, I'm going to lose 1 double bond. When I do the last hydrogenation, I'm going to lose all the double bonds. It's complete hydrogenation. And when I do complete hydrogenation, I'm going to form 3,7-dimethyl. Why? Because my dimethyl is carbon number 3. Remember, the carbon number 1 is hydroxy group. Carbon number 2, carbon number 3 is the first methyl. The other one is 7. So we are having 3,7-dimethyl octanol. Now, if you look at it, you're telling me that the last ring is double methyl. No, it's continuation of the ring. Continuation of the ring. Let's count. Carbon that bear hydroxy group is carbon 1. Then carbon 2. That one that is like a spiral is carbon 3. Then we have carbon 4, 5, 6, 7. On that 7, we have methyl. And the last bond is the 8. So that's why we have octa. Octanol, because it's an alcohol. So in the alcohol, we have 3 and 7 that has methyl. So complete hydrogenation of nerol or geranyl is going to give us 3,7-dimethyl octanol. Is that clear? That is number 1 scheme. Now, another scheme you might be asked is, Now look at, we have another one. How do we obtain menthol from geraniol? Let's follow the scheme. And we are looking for menthol. Where do we get menthol from? Are you following the scheme of menthol? Now, let's move from citral. Have you seen citral? Where they say number 1, citral under hydrogenation, what will it form? It's going to form citronellal. Then when it cyclizes, what will it form?
Isopolygous.
Then under hydrogenation, what will it form?
Menthol.
Menthol. You can see. So that's another scheme you're going to note. The first one is how to form 3,7-dimethyl octanol. The other one, how to form my menthol. And the first one I'm going to come from. Now, even if I was asked how to form 3,7-dimethyl octanol from citral, we can do it. Yeah. Right? So it means that from citral, I'll hydrogenate to form geraniol. I also hydrogenate to form citronellal, and then hydrogenate again. So all these things are hydrogenation. The only place we're having cyclization is when we are forming a menthol. You can see how simple these things are. So it depends on the question you are asked. You understand that what you're doing, that you're doing hydrogenation or you're doing oxidation. So look at it as if you make things.
Ma, please, I want to ask a question.
Do.
Okay, please, when they ask us this question, are we to also draw the structure as we are?
Yes, in this particular one, you're going to draw the structure. Because because the structure will even help you understand what you're doing. Sorry, if you don't draw the structure, you will not understand. How will you know that it's 3,7? If you don't know that all the hydrogen has gone. So how will you know it's menthol if there is no cyclization? So if I want to form my menthol from citral, what I will do, I will hydrogenate citral. Remember, citral is the aldehyde part of it. Then when I hydrogenate it, I'm going to form saturated citral, which is citronellal. Then that citronellal, there will be cyclization. When there is cyclization, what happens is that there will be a movement of this double bond. So when they move, they're going to release hydrogen that will form hydroxy group, and the ring will close. Then when I hydrogenate, what am I trying to do when I hydrogenate? Because there is one double bond already. That double bond needs to go for me to form my menthol. And now from my menthol, I can also go further forming menthol. What will I do? What will I do if I want to form menthol? For menthol. Oxidation. So I want us to understand this is just going to make you to have to bring chemistry to life, because you're like connecting all your chemistry together, right? So now if you're asked, okay, you have menthol, I want you to form menthol, you want to start asking, where will I get menthol from again? Because you know that that's why the structure is important. I've seen the structure of menthol. My menthol is just that I want to oxidize. So I'll just put oxidation sign and I'm good to go. You're not serious. So any question on this? So the two steps I want you to know here is, now look at if you look at 3,7-dimethyl octanol, meaning that all the double bond has been saturated by hydrogenation. Then if you look at 3,7-dimethyl 2-octanol, what does it mean? What is the difference between them? It means that one of the double bonds was saturated, and one was there. That's why it was 2-octanol. Do you understand? So these are very, very simple. So 2-octanol. Now, if you look at now from citral, you can see arrow that went down. Under hydrogenation, we have 3,7-dimethyl 2-octanol. Then when I form 2-octanol, meaning that I've done further hydrogenation. So these things are very simple. What you are virtually doing here is hydrogenation, hydrogenation, hydrogenation. Everything you're seeing here is hydrogenation. So it seems that I can hydrogenate my geraniol from one and form so many compounds out of it just by simple hydrogenation. The only thing different that we did is when we moved from citronellal to isopulegol by cyclization. That's the only different thing we did. Every other thing is hydrogenation. Remember, hydrogenation is a reductive reaction. So we are reducing it. When something is unsaturated, you want to reduce it to saturated. It's a reduction. So hydrogenation is a reductive reaction. So that's how simple this. So now, because we're going to do class work, which we're going to turn in as assignments. So if you're asked to synthesis of 3,7-dimethyl-octanol from geraniol, you should be able to write it and draw the structure. And if you're saying, how do you obtain menthol from citra? Even if I say, how do you obtain menthol from geraniol? You can do it. So there's no big deal about this. Let's go to the next slide. If you have questions, let me ask your question. This is another conversion. We are converting monoterpene to other monoterpenes. We are converting limonene. Now, the question that you might be asked here is that, how do you convert limonene to p-cymene? This is one of the things that we like too much. I don't know why we like it too much. This paracymene, we like it too much. But it's a simple thing. Now look at it. Now, whenever I see some of this structure, what I want you to do whenever you're reading is that, as that's the sense of being in the class, some of these things I said, you might be asked this, you might be asked that. And the intelligent student will be putting it down. Because I'm giving you A's for indirectly. That's not how you enter exam, you will not see this. So those ones you even here say you will see. Have idea of them, kata kata. So that whenever you, even if it's not all of them that will come, at least when they come, you say, ah, thank God I learned it. Right? So now when you have a limonene, remember, limonene, is it cyclic or acyclic? Is it mono or bicyclic terpenes? Mono. 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 This is mono. Now, I'm forming mono. So whatever we are doing here is, if you look at every compound here, is the same class of terpene, is mono. They want to convert this limonene to another compound. And if you look at the final compound, which is paracymene, what difference is just like the hydrogenation? The previous slide, we are talking about hydrogenating, right? Moving from double bond to saturated. Here we are removing hydrogen. That's how we are moving from saturated. We are increasing the unsaturation. We have limonene has just one double bond. We ended up with 3 double bonds. So that's what we call it conversion. Now, if you look at all the arrow, we are using what? What kind of arrow are we using? Reversible arrow. We are using reversible arrow until the last phase. Then we are going to form our paracymene. It means that I can follow the route of gamma terpenine, or I can follow the route of terpinolene. I can also follow the route of alpha terpenine. So anyone is fine by me. So the first stage I want to do, which one do I want to follow? I want to convert limonene to paracymene. Do I want to follow gamma terpenine or alpha terpenine or terpinolene? Anyone that I want to follow is fine. Nobody wants you to follow all the routes. Just look for the one that is simple for you and follow. Now, if I want to follow the gamma terpenine, I'll have to first of all form the transition state. Transition state is the intermediate before the gamma terpenine. So when you get to your gamma terpenine, you dehydrogenate to form your paracymene. Now, the same transition state is what we are also going to employ in alpha terpenine. But the difference is that my transition state is adjusting. That's why we call it alpha. This one is gamma, because of the presence of where this positive sign is located. Okay. Then if you look at the terpinolene, Tapinoline, we did not have any transition. We have movement of bond. The bond that was in limonene changed position in tapinoline. So any of them that is found by you, follow. So I can move from the transition state of alpha tapinine to tapinoline. I can move from the transition state of gamma tapinine to tapinoline. So any of them is fine, because what happens is that positive sign can either go up or come down. If it comes down, it's moving from alpha tapinine to tapinoline. If it's going up, it's moving from gamma to tapinoline. So any routes, just discover one that is feel that is this for you to go, and just know it. It can't be more than 3 steps. First one is limonene, transition state, gamma tapinine, then dehydrogenation. So that is it. Any question on this slide? No question?
No, I don't understand.
What don't you understand? Thank you.
Like for the limonene. What about the other steps?
Which other
ones,
steps?
like the starting maybe.
Who is talking? Let me talk. Let me know you.
Aisha.
Aisha. Aisha, are you in this class?
Yes, ma'am.
Are you sure you're not doing something else and you came back and realized that they passed you and you want to tell me? Because I don't think anybody will tell me how about the intermediate. Who can help me answer her question? Victor, unmute yourself and answer Aisha. Aisha said she does. Aisha, ask your question again.
Like, what about the intermediate? That's what I'm asking. I don't get it.
What about the what?
Like from the limonene we get to P-cyanine. Like, what about others?
You're not looking at the arrow. Look at the arrow very well now. It's the limonene that the limonene is the starting material. Then we can have 2 intermediates. Can't you see the transition state? The one up and down. Can't you see the arrow? Arrow is telling you what is happening. So they can go up and down. That's why it's reversible. That transition state after limonene can also change to the transition state down for alpha tapinine, because it's a reversible state. So that positive sign can move up. Then tapinoline is an intermediate between both of them. Can't you see the arrow from gamma tapinine going to tapinoline, and the arrow from alpha tapinine transition state going to tapinoline? So all of them are going to have transition states. So it's like this alpha tapinoline is in the middle of them. It can be up, it can be down. But it depends on the movement of arrow. Now, from your 322, when this positive sign is moving up, remember, we are for it to form a bond, there's a movement. Do you understand? So is the movement, if the movement is going up, it's confirmed alpha tapinoline from gamma transition state. If it's moving down, the positive sign is moving down. It's forming from alpha tapinoline, alpha tapine to tapinoline. So everything. So what we need to talk about is that I can move from my limonene to gamma after the transition state of limonene that will form gamma tapinine. Then I will dehydrogenate to form parathymine. Or limonene, I'm going to move to a transition state that would give me, any of the transition states can give me tapinoline. Then when I hydrogenate, I'm going to form parathymine. I can also move from limonene, form transition state for alpha tapinine that will dehydrogenate to give you parathymine. There are how many routes? 3 different routes. So anyone that you are conversant with that is simple for you, note it and follow it when the question comes. Are you okay, Aisha?
Yes, ma. Thank you, ma.
Are you sure you're okay? Or you don't want to accept, so we can continue. Are you okay?
Yes, ma.
Okay, well, let's continue. So this is another slide. This is a reduction reaction of carbon. So I will not bore your head with this, but just understand what is reduction. It means that this carbon can reduce using different reagents. it can reduce using different to form different compound, meaning that the reagent determines the compound formed. Now look at our starting material is a carbon. Because of ONE, meaning that it is a ketone functional group. So when it reduces using hydrogen at a very high pressure and nickel and oxide, is going to form that ketone is going to form hydroxy group, and the double bond will be saturated. So it's doing both hydrogenation and reduction, because hydrogenation is reductive reaction. So it's going to hydrogenate the double bond and reduce the ketone to alcohol. So just for you to understand, then when I'm using hydrogen in palladium and calcium carbonate, what am I doing? I'm doing the reduction of only the double bond. So when I'm reducing using zinc in acetic acid, I am doing what? I'm doing only the double bond. So when I'm reducing using sodium borohydride in cerium chloride, I'm doing what? I'm reducing only the ketone functional group. When I'm doing potassium hydroxide in ammonia, I'm going in amine, I'm going to reduce what? Only the ketone is cleaved out. So now the issue is that whatever the reagent I'm using determines the product I'm forming. So nobody wanted to know all these things. So this is what happens when carbon is reduced. So the reagent determines what happens. So potassium hydroxide in hydrazine is going to do cleavage of the ketone, and double bond will remain. Other ones is either both of them are being reduced or one is being reduced. So that's just that. So that's all about here. So there's no big deal about it. But at the first time when you see it, you say, what is this again? What is this? This course is full of structure. What structure is this again? So there's no big deal here. And you might not even be asked about it, but just understand that in reduction, your product is determined by the reagents. So in this case now, we can have so many things. So if they okay, name one a reduction reaction of carbon. You can use anything. Okay, but don't disturb your head. We will not give you any question that will make you afraid. But understand it so that tomorrow when you are teaching somebody, you understand what is happening on this scheme. The reduction is determined by the reagents. Just like, remember, oxidation is also determined by the reagents. That's when I use my PCC, I'm saying I'm doing selective oxidation. And when I'm putting my permanganate, I'm telling you that I'm doing complete oxidation. So that's the sense of knowing all this. Let's go to the next slide. Any questions so far? Okay, let's continue. Any questions? Okay. Now, we've done monoterpene. Remember monoterpene, how many isoprene units do we have in monoterpene? How many isoprene units do we have in monoterpene? 2. What is the precursor for monoterpene? What is the precursor for monoterpene?
Geranyl diphosphate.
Diphosphate.
It's not diphosphate.
Geranyl diphosphate.
Geranyl. Please just get conversant with this. I'll be asking so that I get familiar with them. Because when you're familiar, when you enter exam hall, exam will not just be like classwork for you. So follow me, okay? Whatever I say, just note those things I'm talking about. It will help you. So that's the benefit of being in class. Now we're talking about, we say we have monoterpenes, we have acyclic monoterpenes, and we have monoterpenoid. What's the difference between monoterpene and monoterpenoid? What's the difference? Monoterpene and monoterpenoid. What's the difference?
The oxygen.
Oxygen.
Yes. So whenever we're talking about terpenoid, we're talking about presence of oxygen. Now, from extraction method, what are the method of isolating terpenes? What are the two methods we talk about? We use to isolate terpenes from plants. or from animals? What are the two methods? These days, I'll be attaching mark in my notebook.
Sourceless extraction, distillation.
What kind of distillation? It's not just distillation.
Steam distillation.
And then hydro distillation. Please talk about hydro distillation. Hydro distillation, sourceless is there, hydro distillation and steam. But when you're talking about essential oil, we deal with more of hydro distillation and steam distillation. So now we're going to sesquiterpene. How many isoprene units do we say sesqui has? Some of you like Expo very well. You like Expo very well. Even like I said, the people that are perusing, they use their eyes to get the answer before talking. You can see I caught you people that you are doing Expo. Now, these are obtained by steam distillation. They are compounds that are obtained by steam distillation. So it means that hydro cannot get it. They need plenty heat for them to come out. And remember, these isoprene units are linked together by head to tail. Head of first unit connect to tail of the other one. So the other head connect to another tail. So that's how they are forming. And we say these are mostly found in plants and fungi. What are fungi? Are they animal? What are fungi? Fungi and
They are microorganisms.
Yes, they're microorganisms. So now these sesquiterpene are very minor. The major component we have is monoterpenes. Now I forgot to tell you guys that we are the co-host in this class. Anybody disturbing me in the class, remove the person. Now, limonene is that thing that gives your lemon the most active component in lemon. What makes lemon is limonene. Limonene is that compound that gives lemon the potent antifungal, antibacterial activity. Now, limonene is also what, whenever you talk about lemongrass, the smell. So it's a very good, it has so many benefits. So limonene is very, very important when you're talking about essential oil. Now, remember I said monoterpenes are the most abundant, and we obtain them mainly by hydrodistillation because some of them are very volatile. So we pamper them. But the ones we're talking about sesquiterpenes, they are minor. They are typically very minor components. They are not like monoterpenes. Like no menthol now, when you're talking about mints, and you're chewing your gum, you said, I'm not the one that has menthol. You don't understand. You know that. So if you feel the structure of menthol and I see you chewing gum, I'm going to seize your phone. Because you cannot be chewing gum and you saw the structure of this menthol in your gum. You don't want to cram it. So that menthol will come out in itself. Want to know people, and I'll make it a compulsory question. Now look at the example of sesquiterpenes. Now, in this, the first structure we have is what? Farnesene. Farnesene, is it cyclic or acyclic?
Acyclic.
Acyclic. Why is it acyclic? Because the ring is not closed. Okay. So we have farnesene. Now you're understanding it. You can see this course is very interesting. But your eye will be down. You will not be yeah. If you do yeah, you will not understand the course. You have to calm down. Be calming down. So we have farnesene, we have moroline, and we have malsonone. So at least by the time you know farnesene, sesquiterpene, you'll be fine. So sesquiterpene, we have farnesene, and we have moroline. I would have implored you to go back through the past questions. Who are the people that have seen the past questions? No, but none of you have seen the past question. Victor.
I've seen the past question.
Okay, good. So I want you to, if you have a copy, share it on the platform. Let's look at examples of sesquiterpenes. More example. Okay. Look at more example of sesquiterpenes. We can see we have farnesol. Now, difference between farnesene and farnesol. Go back to the previous slide. What's the difference between farnesene and farnesol? What's the difference? If you look at it, just the hydroxyl functional group, that's just the difference. So it means that if I want to talk about, I can talk about two compounds to be farnesene and farnesol. There are two compounds, and there are two sesquiterpenes. So you can see this, whenever you know one, you know the other one. Another one I want you to know is caryophyllene. This caryophyllene is a very important component in essential oil. Caryophyllene is a very good and important component in essential oil. I think in the next slide, you're going to understand that we like this caryophyllene so much. I don't know why, but we like it. Maybe because of this, its medicinal potential. Maybe that's why we are always interested in it. So we talk about udesmol and others, as you can see on this list. These are all sesquiterpenes. If you look at them, they have 15 carbon atoms, making it that they have 3 isoprene units. The next slide. So what are the benefits of this sesquiterpene? That's what we're going to end today's class. What's the sense of sesquiterpene? What are the role of sesquiterpene? Now, number one thing you should know that these sesquiterpenes, they have the deleterious property, which we refer to allelopathy. They are used to control other plants. Now, there are some things that when they are like whenever you spray them, some plants, as in you're going to control some plants from growing, as you're going to kills plants. Now, they kill plants. They also have antibacterial property that is on human system. They are used by fungi to break down plants. Remember, fungi is a very important, there are good fungi. So they are used by fungi to break down plants. We call them phytotoxins. So some of them are very toxic. They are used by fungi to break down plants. Phytotoxins, they are toxic to plants. And they're also used as defensive chemical. They're used as defensive chemical by plants against insects and animals. And for animals, that's fungi. So that is like some plants that you see that ants can never climb on them. You will never see ants. Even if the neighboring plant has ants everywhere, this plant, ants cannot climb on this plant because of this sesquiterpene in them. So it will be, ants will be running away. Fungi cannot grow on them. There's some extract you have, even with ordinary water, that extract can never grow fungi because it contains this sesquiterpene. It's this thing is not spoiling because of this sesquiterpene in it. This fungi cannot grow, even insects cannot pass through them. So that's the role of sesquiterpene. We have allelopathy, we have phytoalexin, we have phytotoxins, and we have defensive chemicals used by plants as defensive agents. So what are the benefits or role of sesquiterpene? You should know that. Why sesquiterpene? Why do we really need? Remember, they are not very common. That's why there is not every plant that you see that no ant is around it. There are few because they are very rare. Because they are very rare, their work are very, very numerous. These are the compounds that have antibacterial properties. That's why I was talking about caryophyllene. They have antibacterial properties. Things that is some of the things that when you use, they say, this thing is very good, or it can cure you this, it can cure you infection because of the presence of this sesquiterpene in them. So I think we're going to end the class today, so we can start. When is the next class? Monday. So I'm going to send the assignment as what we've done so far today. So we'll continue on Monday. Any question? Please, I want you to ask question. What you don't understand, ask your question. Please, Precious, Victor, take attendance. Jessica is not in class today. Jessica is not in class today. Some people are not in class today. But remember, anybody that is not in class will not submit assignment. But I will not access the assignment. They will go and copy. They will go and copy. If we don't know that, I know students that are committed. Think I don't know them. I know them all. I normally go through all the attendance before you submit. So whenever you want to do Ojoro, I go catch you. Is Anna here? Is Anna in this class? It means Anna is not in class. Can see how I'm catching all of you. I'm catching all of you. Is she in?
Are you in class? So I don't see your name here. You don't go enter attendance.
So I think there's no question, right?
Class.
Like I normally encourage you guys. This is an A course.
Ma, I want to ask you a question.
If you don't have 80, I'm going to deal with you. I'm looking at
Ma,
all
I
of
have
you
a
like,
question.
Ella, ask your question.
Ma, my name is
Professor Ella.
Gabriela, ma. My name is Gabriela.
Ella now, Gabriela. It's not Ella with the end of Gabriela.
Ma, I don't mind out.
Oh,
There's Noella and there's Gabriela. Me, I'm Gabriela.
all of them are Ella. Ella. Ask your question, Ella.
So, ma, hey, I just want to know the difference. Like the camphor that you spoke about, you said you go to market, we'll see camphor. Is there a difference in the round and the square camphor?
Now, the normal camphor that we are talking about here is the one that repel insects.
Okay, the round one.
That is, yes, the one that you use to repel insects.
Okay.
That's what we're talking about here. Okay. So is that one of block one? I don't know about it. The one I'm sure of is the one that repel insects.
Very well. You have another class now.
Thank you, ma.
You leave it now. Bye.
You're welcome. Any other question? Please.
No, ma.
I want you guys to aim at. Your picture is fine. Agosu.
Thank you, ma.
But if you don't have A in my course, you'll be my enemy. So please make sure you are free to ask your questions. Even the question, we've done three classes now. Make sure you ask questions on these 3 classes. No matter how funny the question may be, it's because you don't know, that's why you're asking. Remember, it's part of your school fees. So don't be shy in asking questions. If you don't want to ask questions on this platform, ask to my page, on my private page. But the most important thing, I want you to understand it. Don't cram it. Don't start reading at the 11th hour. And at the way you enter exam hall, you see Citra. It will be like Nero. All of them will be mumbling together. You see, you will be confused about the difference between Nero and Nero. So the more you do this, remember I said there must be hand-on. Make sure there's an interaction between your brain, your pen, and your paper. in this course. Now, announcements. For those that did well, I'm going to generate the broadsheet. If you know that you did well in some courses, you have very good grade, you are the highest in a course, you're going to get a gift. We are not doing any cake again. People that have a very good GP, they're going to get a gift. Okay, so they will get a gift. So my students, not for everybody. So the essence is that now whatever we are going to give you is not what you're going to eat, it's what you're going to use to write. So whenever because they said the rewards for hard work is more work. So appreciating you for A you have, we want you to write and have a better A. So at the end of everything, we'll celebrate you more in a grand style. So thank you for joining the class today.
Ma, when can we check the broadsheet?
No worry, I will update you before next class.
Right student on the top.
You will know before the next class, okay?
Okay, ma.
All right, thank you very much for coming. See you in next class. Make sure you turn in your assignments at when due.